Hi everyone. Rebecca Skinner is a software engineer at Mercury and author of the forthcoming book Effective Haskell. She is passionate about teaching functional programming and helping the Haskell community. And today he has his work us through the type level programming. Over to you, Rebecca.
Hi everyone. Let me go ahead and get these slides going. So thanks everyone for coming to listen to me talk. Today we're going to talk a bit about type level programming, and I think that a lot of the ideas that we're going to go over here. I guess before we get started, there's this QR code down on the bottom of the screen here, and if you follow that or go to rebeccaskinner.net, you'll find an article with links to the source code that we're using in this talk, as well as a write-up that's going to go into a bit more detail, because we're going to go through stuff a little bit fast. And just a bit more background about me. I'm Rebecca Skinner. I work for Mercury and we're hiring, but right now I'm just speaking as an individual. I'm not representing the company. And I do hope that you'll keep an eye out for my book late this year, early next year. So a bit of background on this talk and how this got started was earlier this year, I got the idea in my head that I wanted to make my XMonad desktop look nice. And I was a little bored, maybe because of the pandemic, and I thought to myself, well, I wonder if I can really apply some type level programming to the way that I'm setting this up, because if you haven't used XMonad before, it's a desktop environment for Linux, and you recompile it whenever you make changes. And so the idea that I could guarantee that my environment was set up the way that I wanted every time I go to recompile it to switch things around was really appealing, because it would make sure that I wouldn't ever build a version of my desktop that wouldn't load. And what I found as I was working through this was not only did it work pretty well for me as I was trying to configure this desktop, but it also was a good example in general of a number of the concepts that come up when you're doing type level programming. So I was hoping to just share with you all some of the concepts that I put together. So let's get this out of the way, right? Like on the surface, a theming system, it doesn't have to be all that hard, right? What we're really talking about is some sort of a mapping of like some themable elements to some colors. And we could just do it like this. We have some maps here with keys of all the different things that we might want to set a color to, and we're just using some hex strings. And you could do it that way, and that would be fine. A big problem with that approach is that every time you want to change something here, right? Like you're going to have to change things everywhere if you want to keep a consistent color scheme. And things look nicer if we're consistent. So we could define a color palette that lets us give useful names to different things. Like we can say foreground color or background color, and we can use those uniformly whenever we want a foreground or a background. Similarly, we might say, okay, well, strings are not very helpful if we wanted to find colors, because they have a pretty fixed format. So let's just make a normal record here that holds each color channel, red, green, and blue. And that will get us, we could say this is our 80% solution, right? Like this is pretty good. We can call things by their name, and that gives us consistency. However, there are a few non-optimal things that we have to deal with. The first is that everything that we want to pass this dictionary, this color palette into, has to agree on what it's going to call things. So if I'm writing all of the components myself, I can say, okay, well, I'm going to use the word foreground. But if I want to import a library to add some capabilities, maybe it doesn't agree with me about what things should be called. And that can make it really tricky, right? Because you're gonna, again, hit some runtime errors as it's trying to look up things in that dictionary that maybe weren't available. The other thing is sort of related, right? Like we have this dictionary, but we don't really know what's being used, which means that we might accumulate cruft over time, and it would just be really hard to update things. And finally, we don't know if this is going to work. A map is a runtime value. And in the best case, right, we're going to have code that safely throws an error message if it can't find something. In the worst case scenario, we just crash. So can we use the type system to make this better? I think we can. Let's look at some of the ways that we could do it. The first thing that we could do if we're using the type system is we can have it tell us what things are being used. For example, if I call a function, I can have the type of that function inform me of what elements of a given theme that it wants to make use of. And also, I can make it a compile time error to try to give it a theme that's missing some of the things that it wants. And that will help me both make sure that I have an easier maintenance path because I can see exactly what's needed and eliminate things that are no longer being used. And I can also ensure that I'm not going to get a runtime error because I'm missing a color that's needed in order to draw something on the screen. And here's a little example of what that might look like. So I have this thing called color demo, and for the sake of the talk, we're not going to actually draw a bunch of windows on the screen, right? We're just going to print out a thruple of our red, green, and blue. And so I'm calling this thing called lookup color, and we're giving it a theme, and that's going to be all of our colors. And then we're passing it the color that we want. In this case, red, green, blue. It could be foreground, background, highlight color, or whatever. But we're passing this argument a little bit differently than you might have seen before. This @ sign means that we're using type applications. And so these strings here, they're actually type level strings. And we'll learn a little bit more about how those work later on. But let's dig into the type signature of this color demo. You can see here that we have has color. This has color type class constraint. And so we're saying has color red of theme, has color green of theme, has color blue of theme. And now we can see exactly what is being used for our demo. And an important thing to note here is that this type actually can be inferred, right? So it's not that we're explicitly thinking ahead of time about what colors we want to use. We can write the code that we want to style things the way that we would like, and then let the compiler tell us afterwards what we need in order to satisfy that. So we have this theme instance. That's the type of the theme that we're passing in. But what is that, right? Like, well, it's some sort of a map of a string to some sort of an RGB value. And we'll throw it in a new type wrapper just to make things a bit more convenient as we're adding some features here. And the problem here is we need to ensure that the theme actually keeps track of what elements are in that map. So we're going to add a type parameter. And that type parameter is a phantom type. We're not using it anywhere in the value of the theme, but we're using it only at the type level to help us keep track of the colors that we need to have in the theme. So let's make one. Here I've defined an empty theme instance, and its type is a theme instance of a tuple of an int and either a string or a bool. Well, that doesn't seem like it makes much sense. That has nothing to do with the theme. So what we'd really like to do is we'd like to say, okay, a theme instance has a type parameter called theme, but we're limiting what that type parameter can hold. And we're saying that it must only be something that is actually a valid theme. So we're going to add a kind signature, and a kind signature looks a lot like a type signature, but it's the type of a type, right? So a kind lets us constrain types the same way that types would let us constrain values. So now a theme instance is going to have a type parameter, but that type has to be a theme. So what is a theme, right? Well, we know it's a parameter to a theme instance, but if we're going to pass one in, we have to know what it is. Well, it's a collection of colors, and it's a collection of colors that we're going to know at compile time, and we can refer to them with some sort of a name. And one of the ways that we could define a color is just with regular data types like red, green, and blue. And we could do that. We will do that later on in this talk. We'll show you how we can make use of this. But as a first class way of referring to colors, it's kind of a pain, right? Because we would have to enumerate every single color that we might want to use, and that's no good. So we're going to use symbols, and a symbol is just a string at the type level. So every symbol is its own type, but we can write them just like we can write any other string with quotes, and that's a symbol literal. One of the really great things about using symbols at the type level is that we have this known symbol type class. And when we use known symbol, it gives us a way of bringing a type level string down into the value level. So we can define something at the type level like the symbol green, and we can also use that at the value level when we're trying to do something like, say, look up a value in a dictionary. So this is one of the really key things that we're going to be doing throughout this talk, is figuring out ways to make the type level and the value level actually work together and be sort of cohesive in this way. And that's great. We just defined what a color is, but we want a theme, not a single color. So we're going to say a theme is a list of symbols. And this probably looks pretty familiar. It's a type alias to a list of symbols, but a symbol is a kind. It's not a type. And a theme is a kind. It's not a type. So what we're actually doing here is we're making use of this data kinds extension that lets us define kinds using the same syntax that we would use to define types. And this is going to be another thing that we're going to do pretty regularly whenever we're doing any sort of type level programming. So we have this type level list, but we also have this thing called hascolor. And hascolor is going to say, okay, well, we have this color name and we have this list of colors. Is the list the right list? In other words, does it actually have the color that we need in order to satisfy this constraint? And so we have this hascolor type class, and it has two parameters. It has the color that we're looking for and the list. And we're going to implement it with type class recursion. And this is something that we're going to do all the time when we're writing stuff at the type level. And it works pretty much just like regular recursion, right? We're going to start with a base case. So what is the base case of looking for something in a list? Well, it's that we found it. In other words, that the head of our list matches the thing that we're looking for. And so we're going to define an instance for that. And you'll notice here something that is a little bit different from what we would write when we're dealing with value level Haskell. And that's that we're using the word color twice, right? So our symbol, we're calling that color, and the head of our list, you can see that we're just using a colon to destructure our type level list here. And so the head is color. And we're actually guaranteeing in this case that those are the same type. So if color is the string, the type level string green, the symbol green, it must be the same in both cases. And so what's our recursive case? Well, our recursive case is going to be the situation where the head of our list is not the color that we're looking for, but the remainder of the list does contain the color that we're looking for. Because when we're working with type classes here, there's no sense of like returning false, right? We can't create an instance that says that it's not an instance. So we have to be very mindful to only define instances for cases that should match. So the only way that we can write an instance is if the immediate case matches or if the overall list matches. But we do have a problem with that implementation right here, and that's that in our second instance, we're saying we have a color and a current color. And while our base case ensures that we have a match because both of the times that we're using color, we're guaranteed that they're the same type, in the second case, we're using color and current color, but we have no guarantee that they're different, right? So this is the same thing that you might run into if you have a value level function from A to B, right? We're saying like, okay, well, A and B could in principle be different, but that doesn't necessarily mean that they must. And so the compiler is going to realize this, and it's going to say, hey, I have an overlap. In the case where these two things are the same, I could either match that first instance or the second one, and both are valid. And so what we're going to do is we're going to use this overlappable directive. And what that's going to do is that's going to tell the compiler, hey, when you come across these situations where something might conflict, pick the other instance. And we have another one called overlapping, which says pick this one. And there's overlaps, which I generally would say try to avoid because it's like saying either pick this one or another one. And you're a lot more likely to run into problems with that. It's nice to be explicit. So we have Haskell, right? And you'll notice that there's no function associated with this type class. We're purely using the recursive nature of the instance to validate that the constraint has been matched. We don't need any functions associated with that. So we can guarantee that we have a color in a list. We can get that color by name. And so let's look at lookup color, right? How can we define it? Well, we have guaranteed that theme instance has some list of colors and that list of colors contains the color that we're trying to look up. And so all we need to do is index into our map with the runtime representation of that color type that we passed in and get a value out. And this works, right? I can call demo theme instance. I can give it this list of red, green, blue with a map. And if I look something up like red, I get a value. And more importantly, if I look something up like yellow, I get a compile time error, just like I would hope, because yellow isn't part of that list. And this is a little bit ugly, right? These error messages, we can make these better, but unfortunately, we're not going to have time to dive into that in this talk. So we still have some opportunities for improvement, because one of the issues is right now, we can define a theme instance, and then we can look up a color that should exist in that theme instance. So I'm looking up blue. Blue is part of my instance, but I'm getting a runtime exception. And the problem is that I've defined a theme instance that has only the color red, and I've told the compiler that it has red, green, and blue. So the problem is that we're not constructing the theme value and the theme type together. We're doing these separately, and this gives us an opportunity to introduce errors because we can easily forget to add something. If we're only dealing with 3 colors, yeah, we probably wouldn't. But in a large system, we might have 20 and we might be refactoring it, and it could be really easy to drop something. And not only might we fail right away, we might fail 2 weeks from now when we actually go to use a color that we've forgotten to define. So here's what we want to do. We want to capture all of the information at compile time. We don't want to leave it up to us defining this runtime value inside of a map that could get messed up. We want to capture everything together. And to do that, we need to start by defining our colors at the type level, not just at the value level. And so we can go back to this idea of defining a type per color. And I've done this. If you look at the source code examples on the link at the beginning of this talk, you'll see that we have distinct colors for every X11 color. And it works, but it's a lot of typing, right? Almost 1,500 lines of code just to type out those X11 colors, and we're still limited. We still can't define an arbitrary color at the type level. But what if we could? What would that look like? Well, it would look like this. What we're going to do is we're going to create a type that captures each of the color channels as natural types, nats. And that's a way of representing a number at the type system level in the same way that a symbol represents a string at the type system level. And so the type of an RGB color is going to be determined by the three colors, R, G, and B that we're passing in. And that's great, but we still need a way to represent it at runtime because eventually we have to send these colors to something, right? That's going to draw pixels on the screen, and that can't happen at compile time. So we're going to make a type class called isColor. And that's going to be a way for us to map some type, like an X11 type or an RGB type, to a runtime representation of color. And we're going to do this because a type class is, as you've seen and will see, type classes are the way that we go from types to runtime values. A type class's whole purpose in life is essentially to be a function from a type to some runtime value. So isColor is a function from a type to some RGB function to RGB that will give us an RGB value. And we can define one for our original runtime RGB type. It's just identity. And doing it for those colors in our X11 color palette, it's verbose. We need to hard code them, but it's pretty simple to write. But to write one for RGB color, we're going to run into a problem because I could call 2RGB on like, give me like 975 red, 2148 green, 8 blue. These are not good valid numbers for a color, right? We're using 8 bits per color channel. So really 0 to 255, that's our limit. So we need to make this only work for valid RGB colors. And an easy way for us to do that is to use this extension called constraint kinds that lets us define an alias over a set of constraints. So a valid RGB triple is going to be one where all of the parameters are known nats, which means they're some number, some type level number, and that they're less than or equal to 255. And those are, that less than or equal to there is a constraint. So that's just a type class constraint like anything else. And now we can say that we can only define an instance of RGB color when we actually have a valid triple. And so we know now that our colors are in range, and so we can generate an RGB value here. And this natword 8, this is just taking a type level representation of a number and bringing it into runtime. And again, you can see that in the source code that's linked to from the beginning of this talk. So we have type level representations. Let's go back to our original example. We have these dictionaries. Now we can use type level colors. But this kind of reminds you of a problem that we had earlier, right? Now we're still just passing in arbitrary RGB values, and we're doing it at the type level, so we have a little bit more safety, but we still have that update problem, right? We still have to go and change things everywhere universally. And even if we're using X11 colors with a mixed color palette, that's a big color palette, and those are names for the colors, not for their semantic use. So we need a way to actually take what we've done earlier, this work of naming colors with symbols, and take this work that we've done of defining colors at the type level and put them together into a single cohesive thing. So we need a function fundamentally from some type level representation of a color to its name. And when we're talking about functions from one type to another, we're talking about these things called type families. And we're going to start by looking at something called an associated type family. And an associated type family is a type family that's associated with a type class. So in this case, our type family is the same type color name, and it's a function from A to a symbol, where A is a color, and it's whatever instance we're defining for named color. And so that will let us do something like get the color name for some color. So we can say color name val, and anything that has this like is color definition, we can get a name for it by using color name as a type level function to a string, and we can do that in the type signature. And again, creating instances for like our X11 colors, it's just hard coding, right? The type, the color name of Rebecca Purple is just the type level string Rebecca Purple. That's a symbol, not a runtime value here. For an RGB color, we can also give it a name, and it's a little bit more code, but it's really not too bad. We're just taking an extra type parameter. We're calling it symbol. And then we just define RGB to RGB the same way that we did for our unnamed version. And giving it a color is just passing that name parameter along. So this works. It's a little bit verbose, but it's not too bad to deal with. A problem that we will still run into, right, is it would be great if we could use this ability to get a name from a color universally across all of our type level color definitions, which means that we should also do it for RGB color, even though we're not giving it an explicit name. So we'd like something like color name value of some arbitrary type level RGB color to give us a string, in this case, 00 beef. So we're going to do that by first defining this thing called nat hex. And this is going to be a way that we can start implementing this by defining a function from a natural to a symbol. And this is going to be using a thing called a closed type family. And a closed type family does not live inside of a type class. It's its own thing. And it's a mapping from one type to another, in this case, from natural to a symbol. And it's exhaustive, right? When we define this thing, we're going to define all of the cases. It's not open. We can't add to it later. And that's often what we want. And so we're just going to enumerate these. I didn't type out all of these 15 values, but you can see like we're matching a literal 0 to the symbol 0 up through 15 matching to F. And then we can also make these recursive, right? So what if we have 255? That should be FF. How are we going to define that? Well, what we're going to do is we're going to just divide by 16, right? We're going to step through each of the digits one at a time, and we're going to use a pen symbol, and that's like concatenating two symbols into one symbol. And so we're going to walk through and break this natural number down in units of 16 and build up the digits. And we can see that this works. This is just a GHCI example where we're looking at the kind of nat hex 11. It's B, 250 is FA. But we need to pad these out, right? Because B, that's not going to work. We need that to be 0B if we're going to define like a real hex string the way that we would like that to work. And the algorithm for this is pretty easy, right? We're only dealing with 2-digit numbers. So if our number is less than 15, put a 0 in front of it, otherwise don't. And that seems easy, but we're talking about doing this at the type level. So actually it is that easy, right? We can define another type family to implement if then else, because if we think about it, it's still a function from a type. In this case, we're using type level bools. So true and false are their own standalone types with the kind bool. And if we get true, we're going to return the true branch. And if we get false, we're going to return the false branch. And these are both also types. So we're implementing our conditional logic at the type level. We can use that to write something that looks not all that different than what we would write at the value level. We're going to pad our number by saying if our natural is less than or equal to 15, and that less than equal to question mark, that's a version of less than or equal to that returns a type level bool rather than a constraint. So it's going to return true or false. And if it's less than, we're going to append 0 or prepend 0 to the call to convert our number to a hex. Otherwise, we're just going to convert it to a hex. And then we can implement isColor by taking each of our color channels, generating a padded hex digit, smushing those all together and adding a hash mark to the front of it. And now we have named RGB colors. Let's actually do something with it. So we have these named colors. We want to make use of this in order to build a well-typed theme at runtime. So our type is something that we need to know at the type level in order to validate that our colors exist. But if we want to build this thing at runtime, that's going to be some sort of runtime value. So what we're going to need here is a function from values to types. So we've seen that functions from types to values are type classes, and from types to types are type families. A function from a value to type is what we call a gadget. And it's a really fun word to say, right? Gadget. And a gadget is sort of another way that we can define a data type. And so we're defining one called make theme. And gadgets are sort of similar to regular ADTs, but they allow us to actually specify a type parameter when we're returning something. So we can say, like, we have these two branches of our gadget. The first is we're calling make theme, and we're giving it an empty list. So a new theme doesn't have any colors. Or we can add a color. And so we're going to have some like named color, something that we can get a name for, and the rest of the gadget. And this is just like a type level list, right? We're adding something that's at the type level, that's a color, and we're putting things in there. And we're building both our values of colors as well as this type level list. And now we just need a way to convert that to a theme instance. So we would define some function like instantiate theme, and that's just going to convert a make theme to a theme instance. And the trivial case is when we have a new theme, we just make an empty map. And if we have add color, we're going to pattern match out the current color and the rest of our list. And we're going to say, okay, well, let's just get the name for the current color, create the rest of our theme instance with a recursive call, and then insert our current color value and the name. So we get that color name value. That's the way to get our key as a string out of our color, and we just insert that into the map. And so the keys, the strings at the runtime value are coming from those type level symbols. The values are our color values. And so we're building elements up in the map of a theme instance as we're evaluating or tearing down the values of make theme. And we can see this work. So we have this instantiate theme of a sample color, just red, green, blue here again. And if we look this up, we can see that we're getting back the sort of map that we would expect by building something up at the type level and then tearing it down. So at this point, like, we're done. If all we care about is the type level, then we have finished what we set out to do, right? But it would be nice if we could support a runtime configuration as well, because we don't always want to compile things. It will come at the cost of some safety, but it would be nice to have the option. So let's define a runtime theme instance. We'll use JSON, and keys or color names, values are going to be either RGB colors, X11 color names, or references to other colors in our theme. This will give us some consistency, but it's going to come at the cost of a little bit of complexity. So we're going to parse this into another dictionary, again, of strings to color values. And a color value is going to be either an RGB color or an X11 color, or those reference things. But what's a reference? Well, when we're talking about references in Haskell, we're often talking about readers, and we have a type here that will let us do some error handling, but really we're building a reader, right? And a reader is going to let us read the rest of our theme to figure out what color we should use when we're doing something by name. And it's all right, but it kind of sucks because it could fail at runtime. and it might not fail immediately, just like anything else when we're dealing with a runtime map. And it's not very ergonomic. So we're going to have to run that reader every time we want to get a value. So maybe we define a second data type. We call it strict, and we can strictly evaluate a color. So we can walk through all of that map, and every time we see something that's a reference, we try to look it up. And if it fails, we fail to convert our color. And this works, right? But now we're duplicating our type here. And that might get inconvenient, especially if we're adding other color types. So let's try to do it without duplication. And we'll do that by adding this type family, this higher kinded data type family. And this is a really useful pattern when we're dealing with things like this, where we're parsing some values that may or may not work. And so we're going to make a function from either an identity wrapper around a value to just that plain value. So we're going to erase the identity at runtime, and otherwise we're going to preserve the wrapper just as it is. And so we're gonna pass a parameter to color value, and that's going to be W, because it's going to be some wrapper type, either an identity or a reader. So a reader before we resolve it, an identity afterwards. And so our other color is just going to be the result of applying our higher kinded data type family to our wrapper and our color value. And of course, we're passing W back in because we're going to be consistent, right, about what our color value is. And we're going to do the same thing for our theme config, because otherwise we just end up defining like a strict and a non-strict theme config. And so that works, but we need to figure out what's our color value, what type is W, right? Well, if a color value is referencing a theme config, and a theme config is parameterized by what a color value is referencing, well, we end up with an infinite type, and that's no good. Luckily, we can solve this problem by just ignoring it, or more specifically, we can use a new type wrapper. And so what we're doing is we're kind of like disintermediating. That's a fun word, right? We're inserting something in between our theme config and our color value. And so we're adding one layer of indirection, but it fixes the type problem. So now our color references, if we're referencing things, we're going to reference a raw theme config, which we can pull a regular theme config out of. So we go through like one level of new type wrapper when we're dealing with a reader, but our regular plain fully resolved theme config is just an identity, so all those colors are fully resolved. And now we can strictly evaluate things going from a raw theme config to a regular theme config, and we don't have so much duplication. And we're not going to implement this, but you can look in the source code that was linked from the talk. But we can see that this works. We can load that JSON, and we get a theme config, and everything has been fully resolved. But we'd like to use this with the existing type level code that we have. So how can we make that work? Well, we know that theme instance is some value level thing, but we need to provide a type level theme to make one. And so what we're going to do is we're actually going to work not starting from our runtime value, but starting from our theme. So we're going to step through our theme, and for each color in our theme, we're going to validate that that exists in the runtime value that we are passing in. So we're going to do that with a type class called validate theme. And to validate an empty theme, that's trivial, right? An empty theme doesn't have any requirements. So we can just say, okay, here's your theme instance with nothing in it. If we do have a color in our theme, what we're going to do is we're going to, so here our instance, we're pattern matching out the current color, the head of our theme list. And what we're going to do, this is kind of similar to lookup color that we defined earlier. We're going to get the runtime representation of the color that's at the head of our theme list. We're going to see whether that exists in the runtime map that we passed in. And if it does, then great, we're going to go ahead and just validate the rest of the list. And otherwise, we're just going to throw an error, right? Because the runtime value that we passed in didn't have something that was required at the type level. And so now we know that this type class constraint will enforce that we are correctly providing a runtime value that meets all of the requirements of our theme. And we can use this by defining a theme at the type level. We still have to define our theme at the type level, right? We can get a runtime value that will satisfy that theme or not, but the theme itself is still going to be defined at runtime. And so we can define one of those. We can validate that our theme is going to be correct, and then we can look up some values from our sample query here of red and blue. So we're going to validate our runtime theme that we've loaded from disk with load theme config, and then we're going to try to query it with that sample query that we built earlier. We're going to print it out, and that will work. We have now brought our compile time, type safe, will always work theming system into sort of compatibility with also defining things at runtime. And so we know here that we can load a theme. It might fail, but if it passes this validation step, then we are still guaranteed that everything else will work, nothing else will blow up, and we will get immediate feedback as to whether the runtime value that we tried to load was correct or not. And that's it.
Okay, thank you, Revika. It was awesome.